My project is on RLC circuits. We're going to talk about how RLC circuits are composed of mainly three things: a resistor, which is R, the inductor, which is L, and then the capacitor, which is C. We're going to talk about them in both parallel and series, and we'll find the impedance, the current going through each branch, and then the resonant frequency. First, we're going to set up our problem, and our L equals 120 millihenries, and then R equals 30 ohms, and our capacitor equals 40 microfarads. So first we're going to find our capacitive reactance. So our capacitive reactance is XC in this instance, and we're going to set it up with the equation 1 over 2 pi FC, and that's going to give us our resistance. So we're going to plug in our 60 hertz that we have from the very beginning, and we're going to multiply it against our 40 MF, and we're going to make sure that we use the right units so we don't have to go back and fix anything later. And that comes out to 66.31 ohms. After that, we're going to go to inductive reactance, which is XL, and the formula for that is 2 pi FL. And so that's going to be 2 pi times that frequency of 60 hertz times 120 millihenries. And we're just going to convert that real quick, and that should come out to 45.24 ohms. Next, we're going to find impedance, which is represented by Z, and we know that impedance is pretty much any obstruction or opposition to the electric current that we already have here in our circuit. And so that's going to be found by finding the square root of R squared plus XL minus XC squared. And that's going to give us 36.7 ohms. Next, we're going to find the RMS current in the circuit, or the effective voltage, and this is shown by V equals that current in the RMS times the impedance. So we're going to take our voltage source, which is 12, and we're going to divide it by that impedance that we got, which is 36.7 ohms. And that should leave us right at 0.327 amps. Now we're going to calculate the voltage across the resistor, the capacitor, and the inductor. For the resistor, we're going to use V equals IR, and we're going to use that current that we just found, the 0.327 amps, and we're going to multiply it by our resistor of 30 ohms, and that should give us 9.81 volts. We're going to do the exact same thing for the inductor, and that's going to be I times XL. And so we're going to use that 0.327 amps one more time, and we're going to multiply that with the inductive reactance, which is 45.24 ohms, and that should give us 14.79 volts. Now we're going to calculate the voltage across the capacitor, so it's going to be that current times the capacitive reactance. And that will be 0.327 amps times 66.31 ohms, and that should give us 21.68 volts. Finally, we're going to calculate the resonant frequency. So the formula for that is 1 over 2 pi multiplied by the square root of LC. And we know that at resonant frequency, XL equals XC. So our capacitive reactance is equal to our inductive reactance. And then also we can come down to our impedance and we see that full equation, but if XL and XC are equal to each other, then they will be 0, and Z will be equal to the square root of R squared, which is just R. So at resonant frequency, XL will equal XC, and then Z will also equal R. Here we have a series in parallel. Our resistance is 60 ohms, our inductor is 80 millihenries, and our capacitor is 30 microfarads. We will calculate our inductive reactance by using the formula 2 pi FL. We will plug in the 60 hertz from the beginning, and then the millihenries, which we will convert, and we should get 30.16 ohms. Next, we will calculate the capacitive reactance, which is 1 over 2 pi FC. We will use the same frequency of 60 hertz, and we will multiply it by the capacitance, which we will do 10 to the negative 6 because it's microfarads, and we should get 88.42 ohms. To find impedance in a parallel circuit, we're going to use the formula Z equals 1 over the square root of 1 over R plus 1 over XL minus 1 over XC squared. We'll plug in our own numbers, and we will find that we get 36.39 ohms. Now we will find the current that is flowing into the circuit, and so our IS equals the voltage source over the impedance. So we'll take our 12 volts and we'll divide it by 36.39 ohms, and that should give us 0.3297 amps. Now we will find the current flowing through the resistor, and we're going to use our voltage source over the resistance. So we will take 12 volts over 60 ohms, and that should give us 0.2 amps. For IL, or the current flowing through the inductor, we're going to take again our voltage source and we're going to divide it by our XL, or our inductive reactance. So we will take 12 volts over 30.16 ohms, and that should give us 0.3979 amps. For current flowing through the capacitor, we are going to take the Vs over the Xc, or the capacitive reactance, and so we'll take 12 volts over 88.42 ohms, and that should give us 0.1357 amps. For resonant frequency, we're going to use the formula 1 over 2 pi times the square root of LC. We'll plug in our own numbers, and we'll plug in for L 80 times 10 to the negative 3, and then for C we'll use 30 times 10 to the negative 6 to keep all our units even, and we should get 102.7 hertz. So because 102.7 hertz is our resonant frequency, we know that our capacitive reactance is equal to our inductive reactance, or XL is equal to XC.